The kinematics of constant curvature continuum robots through 3 segments. This is some work done by my PhD student, Yu-Cheng Lee, my colleague here at the University of Dayton, Dave Mishka, and I'm Drew Murray. In this work, we try to investigate the mathematical relationships between the positions and orientations at the segment tips of a PCC, or piecewise constant curvature continuum robot with up to 3 segments. Here's just kind of an idealized version of a continuum robot. This one has 4 segments, and the outline of the talk is basically we're going to add 1 segment at a time. 1 segment, then 2 segment criteria, and finally do the inverse kinematics of a full 3-segment PCC robot. So some quick definitions. You see that our PCC robots have solely bending deformation and no torsional deformation. So if I hold the length constant, you see, and I vary the azimuthal angle, you see that it rolls, has this rolling type motion. Of course, we are talking about PCC robots here with variable length. So some other definitions, the curve that traces the idealized shape is called the backbone. Each of these segments is a circular arc. The circular arcs connect tangentially. And finally, their connection points are called segment tips, or sometimes just tips. 1 segment continuum robots. All right, so you have the standard forward kinematics parameters of the length, the bending angle, and the azimuthal angle. You can put those into your standard rotation matrix and displacement vector calculations and figure out where frame I is relative to I minus 1, and then using standard forward kinematic stuff, figuring out with all the L's, thetas, and phi's where all the successive tip frames are located. In this work, we lean into this thing called the bisecting plane. And the bisecting plane is, of course, the set of points that are equidistant from the preceding tip and the following tip. And using the bisecting plane, we have these set of equations listed in the paper that show the basic relationships between a frame at the end of one segment of a PCC robot and the other end. And you get these relationships on the differences in the X and Y vector of the rotation matrix having to be parallel with the vector that points between the displacements. And then this one about the addition. The point here being that it allows you to get a robot independent statement of the relationship between the frame at the base of the robot and the frame at the end of the first segment. And you can see this vector showing up E, which of course is the unit vector that points between the first and final frames. With that established, we can now move on to discussing the 2-segment PCC continuum robot. And the reachability criterion derived here is that the frame, there's a vector that connects the first frame and the final frame, and there's an axis S that comes from the rotation matrix between here and here. And for there to be a 2-segment continuum robot, PCC, that connects here to here, this statement has to be true. All right, so just a quick example. This shows you that if I have an initial base frame and a second frame, I can't necessarily meet it with a 2-segment PCC robot. This matches the orientation, but this is the closest I can come displacement-wise, or I can match the displacement and I can match the Z vector, but then this is the best I can do orientation-wise. And so we start to derive the relationships in the 2-segment robot. And what happens here is we can define this interim vector, Zi, of this middle frame by taking the initial Zi and rotating about this axis, our axis between I minus 1 and I plus 1, by some arbitrarily chosen angle eta. And for a choice of eta, I can calculate the location of this tip frame. It turns out that if you plot all of the tip frame locations, you quickly observe this is a circle. This is observed in the paper. And not only that, but in terms of these 2 frames, we can develop a calculation that shows us where the center of that tip circle is. So what happens is, for the 2-segment PCC problem, you get a 1-parameter family of assemblies that go from the first location to the final location, subject to the final location satisfying our reachability criteria. And then we move on to 3 segments. So here's a 3-segment continuum robot. And in this case, we have the bisecting planes shown here, all right? And of course, 3 planes will intersect at a point. The observation is, since they're bisecting planes, the distance to each of the tips is the same in every case. So I can write down these conditions, and turns out I can actually solve them. And now, again, this is only in terms of the first information about the first frame and the final frame, but this tells me this location O, which is the center of our tip sphere. Having the center of the tip sphere based on the first and final locations, I can then pick any location I want on the tip sphere, and that tells me where the first frame is. That also generates a tip circle to tell me where I can put the tip of the second segment, thereby solving the inverse kinematics of the 3-segment PCC continuum robot. Here, this is just an arbitrarily chosen circle that I'm moving the tip around for the first segment. It generates this first frame, and then with that information and that information, it's showing me the tip circle. I can then pick any location on that tip circle. So we're just picking one of the locations. And this is now showing you the self-motion manifold for the inverse kinematics of a 3-segment PCC robot that reaches from frame I-1 to I+1. So in this work, we've gone through the reachability criteria and hence the inverse kinematics of a 1-segment PCC continuum robot, then the same for 2 segments, which led to a conversation about the tip circle. Finally, for 3 segments, we identified the tip sphere, and we're able to solve the inverse kinematics of the PCC continuum robot for that situation. Finally, the paper goes a little bit further and delves into all the degenerate cases that might show up as you're trying to solve this system. And for future work, we've been investigating the inextensible PCC continuum robots, the case where L is a fixed length. And so I invite you to come to our late breaking poster where we're discussing the inverse kinematics of the 3 segments that aren't allowed to change length. And we've shown that you can have at least 8 solutions for that. Thank you.